Hi, Rocco. Hi, everyone. Okay, we still have 2 minutes, so I'm just waiting for everybody else. I'm just drawing the picture now. Okay, so good morning, everyone. As I said, put your question on chat. Aaron put two problems, 27 and 59. If you have any other questions, please put them. So, 27, I drew the picture. Let's talk a little bit about it. Please mute. Yeah. Okay. All right. I saw your problem, Luke, number 6, definitely. So let us see problem number 27. What do we have? We have this parabola, y equal, that I drew it in a way wrong, sorry, but that's the parabola, y equal x squared minus 2, and the line y equal to x. And we have this region right here, and the question is to find the area of this region. And as we saw yesterday, we have two ways of finding the areas. We either can cover by horizontal rectangle, so we take upper minus lower, or we can do things by vertical or horizontal, left and right. And every problem is different. Every problem we can treat it in sometimes two ways, sometimes one way is better than the others. It will be our judgment. So ideas, what do you think we're going to do with this problem? Do you guys like to do it with horizontal slices or with vertical slices? Before we start finding intersection point and everything else, which do you think is the better approach? Horizontal. Okay, Rocco said horizontal because you're correct, because. Rocco, can you talk? Okay, why horizontal is better? Okay. Anybody can answer Rocco's question. Why do you think he suggested horizontal? Because his mic is not working.
Because if you do it vertically, there's like no, oh no, if you do it vertically, you're gonna have to split it into two
Exactly. If we do it
integrals.
vertically, we have to split right here. Absolutely. Okay. So because if you do it vertically, this is the region to cover the whole region. The upper one is the x-axis. We don't have issue with that. The lower is actually changing. So we have to split. Can we? Yes, we can. I mean, we will set it up once I do it horizontally. So we can do it. But if we do it vertically, so we have to split. Now, if we do it horizontally, my left curve, is always this parabola. So that's going to be the left. And my right curve is this line. So I really don't need to split. So that's the first advantage of the horizontal. But whenever we have horizontal, it means y will be the variable. It means we have to make sure we can solve easily for x in terms of y. If you cannot do that, we have also to switch strategy. So now here, x as terms of y is clear. Is it easy to solve for x in terms of y in this one? If it's hard, it means we do not do it horizontally. Is it easy to solve for x in terms of y? Yes or no?
Yes.
Yes. That's why we're going to go ahead and do horizontal uh, slices. So to be able to do that, we need a lot of work. We need to find all those points or the intersection. Step number one, we have to express x in terms of y. We have to draw our line and then figure out the area of a typical rectangle and then proceed. So step number one, I'm going to look at the intersection. Intersection point. All right, I need this point here. All right, so I will set, it's easy to set the y is equal. There is no issue in this problem. I don't have to set the x is equal. So this will give me x squared minus x minus 2 equal to 0. I factor things out. X, x. And this is going to give me minus 2 and plus 1. It means x is minus 1 and x is 2. Obviously, that's the one I'm interested in. So this will be a minus 1. And then if I plug in minus 1 here, I get minus 1. If I plug in minus 1 here, I get 1 minus 2 minus 1. I'm getting the same y value. It means I'm doing it correct. So this tells me that. Remember, we want to take horizontal. Means I am more interested in the y value. So this is right here. Minus 1. And this is 0. So this is the interval that I need to cut into pieces to cover the region. Okay, part two is I'm going to take my slice right here. Okay, my vertical slice. So in my mind, this is my little y here. I will call it y instead of a yi just for the ease of the representation. And delta y is this piece right there. So that's my typical rectangle. Now I need the length. To be able to find the length, I need to find x in terms of y. So x in terms of y. So let's see here. So actually, that's right. Find x in terms of y. Because I need the horizontal distance, this one. So I need x in terms of y. Now y equal to x, there is nothing to do about that. We have y is x squared minus 2. It means x squared is y plus 2. It means x is plus or minus the square root of y plus 2. Okay, now which one is the one I need? The plus square root of y plus 2 or the minus? Back to you. When I solve, I get the plus or the minus. Which one fits my region?
The minus.
The minus. You agree with your classmate? Because if I am, that's the region I'm interested in. Right here, my y is negative. So since my region is in quadrant 3, it means my x, which is the left for us now, is the minus square root of y plus 2. Okay, that's the one we're interested in. So here, x is the left x is the minus the square root of y plus 2. So the length of, that's my typical rectangle now. typical rectangle, the length is the left, the right value, which is x, sorry, which is y, minus the left value, which is the y plus 2. So let me make sure we understand. From here to here, that's as a function of y. So this is the right one. It's y, which is the right value, always the right value, minus the left value. Always the right minus the left, the right minus the left, even if they are both negative. So that's the length. The width is the delta y. So the area is the length times the width, which is y minus, that's the right, the left. That's a typical rectangle. Now, the total area is the area is almost the sum. At this stage, I'm thinking about splitting the area into pieces and covering it with the rectangle. At this stage, I feel comfortable. I go back to yi because at this stage, I am splitting my interval. I equal 1 to n. So that's the Riemann sum. So now the actual area is going to be equal to the integral of y, which is the right, minus. Now, of course, we simplify everything in a minute. So far, I'm just making sure the setup is fine, the left. And what is the lower limit? And what is the upper limit? Now I go back to my picture. To cover this region with a rectangle, which interval I need to split into pieces? The interval from -1 to 0. That's the interval I need to split. So right here is going to be the integral from -1. Remember, that's the integral on the y-axis to 0. Everything a function of y. So finally, I will get the integral from -1 to 0 of y minus plus y plus 2 to the power a half dy. Okay? The rest is just find the antiderivative. So this would give me equal to. Antiderivative of that is a half y squared. Antiderivative of y plus 2. So that's since I have an inside function, I take it to the side. I isolate it a little bit. I put u to be y plus 2. I need a substitution because I have an inside function. So this would give me integral of u to the half du, which is we've done many times. It means 2/3 u to the power 3 half. It means 2/3 y plus 2 to the power 3 half. So I isolated this one right here because it's different. So this would give me that plus 2/3 y plus 2 to the power 3 half, evaluated between -1 and 0. So finally, I get the value at the upper minus the value at the lower. The value at the upper is 0 plus 2/3 times 2 to the power 3 half. At the lower, I will have a half in here plus -1 plus 2, it's a 1 plus 2/3 equal, you simplify and you get that. Any questions about this homework, about this example? Please go ahead. Okay, So now we move on. If my memory is right, I have number 6 from Luke and I have number 59 from Aaron. So I look at number 6 and then I move on to number 59. Okay. Number 6, I draw the graph, the following. So I have this one, x equal to y, and another line, x equal y plus 1. And this is 1 according to the book, and this is 2, 1. Okay. Question number 1 is find the area of the region by integrating with respect to y. Whenever they say integrating with respect to y, it means I am taking those horizontal slices. It means y is the variable. So this is part A. Y is the variable. Okay. So since y is the variable, I have to see to cover this region with those rectangle, what should I split into pieces? I have to split the interval from 0 all the way to here. So this is 1 here. Question number 2. Do I have the same left curve and right curve? In this problem, if I go from here all the way to here, the right curve is always this line, and the left curve is always that line. So I don't really have any issue. That's a very basic scenario. So this is my delta y right here. This is my y. So the length of this interval is the right, y plus 1, minus the left, which is 2y. Okay. So a typical rectangle, area of typical rectangle is the length times the width. That's the area. So the total area of the region, I'm going to skip the Riemann sum for that. Area of the region is going to be the integral of, I'm adding those little pieces. Interval 0 all the way to 1. And now the rest is, we simplify the expression inside the integral. I will get 1 minus y dy, which is y minus a half y squared between 0 and 1. So finally, this is going to give me a half, I think. All right. Now, part B is they want us to do it geometrically. What do they mean geometrically? First questions before we do it geometrically.
Instead, you could just use right triangles to find the answer.
Right. Geometrically, it means this is a rectangle. Sorry, this is a triangle. And what's the area of a triangle? Is half the base times the height. Are you with me? Okay, let's go back. Which base, this is not a right triangle, so it's a little bit different. So if I use this as the base, which is 1, the height is going to be from here all the way to here. That's going to be the height. So how much is the height? From here to here, I have 1. So it's half, that's the base, and that's the height from here to here. So it's going to be half. The base is 1. The height is 1. This is the half. Okay, so it's not a right triangle in this case, but the formula is the same. If you use this as the base, the height, if you take the vertex that is opposite to the base, and you find the height from the vertex to the base. That's really what they mean by height. Questions before we do the last problem? Okay. All right, so now we finalize with problem number 57, I think. 59. Okay. So 59, you have to sketch the region. And this is the region. The region bounded by x equal y times y minus 1 and y equal x minus 3. Sorry, y equal x over 3. Okay, and the question is, how are we going to sketch those regions? Because they did not give us the graph, we have to sketch it. This is simple, that's a simple line. So the question is how to sketch a region like this. Okay, let me make a comment how we're going to sketch those regions. It's going to be actually very simple. I'm using another paper just to explain how to sketch the region. So this is x basically. If I multiply this out, it means y squared minus y. All right. Let us say I ask you to not sketch this one. If I ask you to sketch y equal x squared minus x, just on the side. All right, this. We know that this is a parabola. We know that. And so it's parabola going up. And to sketch it easily, it's nice to know the zeros. If I know the zeros, I know how to sketch it. So if I set this equal to 0, and I find that the zeros are zeros and 1. So it's a parabola, have a 0 here. It means it's a parabola going like that. So this is y equal x squared minus x. Are you with me how I sketch this? Now, x equal y squared minus y is actually the same thing, but what you are going to do, you're going to basically kind of rotate it by 90 degrees. Or, so what I mean by that, x equal y squared minus y. The graph here is a parabola also, but this type of parabola, this kind of parabola. So if you want to sketch it exactly, you do the same thing. You say this is a parabola. This is a positive number in front of y squared. It means it's going to be parabola to the right. If this is negative, parabola to the left. The same logic. And to sketch it correctly, you find the values of y where this is 0. So it means you said, okay, when is x 0? So you said this equal to 0. It means y is 0, y is 1. Means that's a parabola like this. X is 0 when y is 0 and y is 1. So you graph it exactly, you graph the other one. That's going to be the graph. Okay, so if you want to sketch x equal y squared minus y, it's also a parabola where the opening is to the right. You find the values of y when x is 0. When you do that, you have your parabola. Are you with me on the graphing? Any question? Now I can go to the problem and the problem.
Professor Elias,
Go
I'm
ahead.
sorry. Is it okay to like switch the axes where
No,
you
it's
have the
because
like?
no, because if you switch the axes, you will have to switch this equation.
Oh,
It
okay.
becomes
So it gets a little.
complicated. Yes, it becomes actually complicated. So we will not do that. It's a good question. A lot of students ask me the same questions. But when we have a lot of functions, which one you want to switch?
Okay, I see what you're saying. Okay.
Sometimes you have a lot of functions. You don't want to start playing with all of them. So we're just going to do it the way correctly. I mean, we're not changing the x and we're not going to change the y. Are you with me?
Yeah. Thank you.
Oh, sure. So x y times y minus 1. The reason the book wrote it y times y minus 1, they don't have to write it this way. I want to write it that way to tell you what are the zeros. It means x is 0 when y is 0 and y is 1. That's why they wrote it this way. They don't have to. So it's going to be a parabola, exactly a parabola going like that. That's the graph of this function. Y equal x over 3, that's just a straight line going through the origin. And now I have my function. Okay, so this is y equal x over 3. And this is x equal y squared minus y. And now I think the problem become easy at this stage. Which type of slices do you want to take? Horizontal or vertical? Quickly. Very quickly, I want an answer. Horizontal, absolutely. Vertical will be, I mean, I already have x in terms of y. If I want them vertical, I have to express y in terms of x, which is very hard in this situation. So definitely my horizontal slices, sorry, my horizontal slices, these are my slices. Okay, now I want my left curve, my right curve, both of them in terms of y, and I want the intersection point. Okay, so we need all of this. This is my left curve. It's already given to me in terms of y. I don't have issue with that. The right curve, I don't have x in terms of y. I need to solve it. X is 3y. So my right curve here is 3y. And it's the same across the board. No splitting is concerned. So that's the same curve. Now I need the intersection point because I need to know which interval I have to split into pieces to cover my region. The intersection point, obviously in this case, I need to set the x's equal. I cannot set the y's equal. So intersection point, I'm going to set y squared minus y equal to 3y. Y squared minus 4y is 0. Y times y minus 4 is 0. Y is 0. Y is 4. So these are the one I'm interested in. So that's a 0. So this point is 4. That's the y component. And the x component will have to be 12. Actually, if I plug it here, I get 12. If I plug it here, I will have 16 minus 4, 12. So at least I'm finding the point correctly. So this is my interval right here. This is here, right here. This is 4. So now I know exactly which interval I'm splitting into pieces, and I know the whole picture right now. So now what's going to be, so the length from here to here, this is my little delta y, and the length here. So if this is y, I call this y, it means from here to here I have y, it's going to be 3y minus y squared minus y. So finally, the area is going to be the integral of the length, the right curve, minus my left curve, and my limit. Always I look for y, from 0 to 4. And the rest is simple. You simplify and then you proceed. First simplify and then integrate. First simplify and then integrate. Any other questions? Great. So today we are going to move to section 6.3. Okay, volume of revolution. Here's very simple questions, the following. Let us say I have that. I take this region. So that's a straight line. I take this region right here. Okay. And I take this region and I rotate around the x-axis. So close your eyes a little bit and think. Rotate about the x-axis. Take this. So we are already in 3D. So you can rotate it. What do you get? What do you think? What do you get? You get a cone. Absolutely. So you take this region and you're rotating it. You get a cone. Okay. Example number 2. Very simple region I'm going to give you. Okay. So all of you try to think about what you're getting. So now let's say I take the following region. So this is a straight line here. So this is a rectangle. And I take this rectangle and I rotate it around the x-axis. What do we get?
Would you get a cylinder?
We get a cylinder. Absolutely correct. So this is a rectangle. I rotate it. We're gonna rotate. We're gonna rotate. We're gonna get the cylinder. Okay. What's the volume of the cylinder? What's the volume of a cylinder?
It's the area of a circle times the depth.
Exactly. It's area of the base. And what we mean by base is this one. That's the base. That's the base. That's what your classmate is telling us. Area of the base, you call it the circle, I call it base. So it's area of the base times the depth. It means from here to here. Sometimes we call it depth, sometimes we call it the height. So let's call it the height because a lot of time it's called the height, but depth is absolutely correct, times the height. Okay, that's the volume of a cylinder. It's area of the base times the height. So what is the base here? What's the area of the base in this problem? And what is the height? I'm going to take you back to the original picture. What's the area of the base? The base is a circle. So the area is pi times the radius square times the height. Okay, so it's equal to, if I go back to this initial picture, where is the height and what is the radius? From where to where? When I take this and rotate it, the radius is from where to where? Can anybody somehow tell me?
The radius would be the distance on the y-axis, and the
Yes.
height would be the distance on the x-axis.
Absolutely correct. That's the radius. That's going to be the radius, and that's going to be the height. That's going to be the prompt. So if I call this R, so that's going to be R, and that's the height. So pi, I will not change it, times the radius squared times the height, but that's the radius, as your classmate said, and that's the height. So this is simple example. So a third example, I'm not going to use, you don't have to write it. Suppose I take a semicircle, simple example, and I rotate about the x-axis. What do I get?
A sphere.
We got a sphere, honest to goodness sphere, a ball. Since we're rotating the whole thing, it means the inside is full. So we're talking about the volume. So the idea of this section is how to find the volume of a cone, if I know the region, how to find the volume of the sphere, if I know that region. For the cylinder, we know it. I mean, we don't really have to. That's the volume of a sphere. So let us see the setup first. I will explain how we're going to proceed and we go. So let's see what to set up. I will write the setting up very clearly and then I'll spend some time explaining. Actually, don't write for a second. Let me tell you what the setup is and explain and then we will write. So the setup is going to be like this. Suppose we have any function. Let me draw a nice function here. That's f of x. Doesn't have to be increasing. I do it increasing just for simplicity. That's a region. And I'm going to rotate this around the x-axis. So I take it and I rotate it. This is the rotated picture. So this one. So I rotate the whole region. This is full. So when I'm rotating it, I'm getting a solid which is full inside. So I'm going to get something like that. That's what I'm going to get. All right. So the question is, how can I find the volume of this region? So this is a big solid. How can I find the volume of the solid? What's going to be the idea? It's complicated. I mean, this is changing. It's not complicated. So what's the idea here? The idea is, I'll take you back to the notion of finding the area of a region. To find the area of a region, our approach was approximate the area by the area of object that we know how to can find their area. So we approximated by rectangle because we know how to find the area of the rectangle. So now if I have a solid, what I'm going to do is I'm going to fill it with simpler solid that I can find their volume. What's the simpler solid that we know its volume? So this is complicated. We're going to fill it with stuff that I know how to find their volume. What shall I fill it up with? What's the only,
Circles?
what?
Circles?
Circles, it's a volume. I can't fill it out with circles.
Would a
Stretch.
rectangle work?
No, rectangle, no, I don't know how to fill it out with rectangles.
We could use a cylinder.
We use cylinders. So it's not quite a circle. We have to use cylinders because cube, no way. Cube will not do it. I don't know how to fill it up with cube. We're going to fill it up with actually cylinders because we know the volume of a cylinder. That's going to be the easiest object. And the question is how we're going to generate the cylinder. But that's why I'm trying to explain the idea. So what we're going to do with is like cylinders, another cylinder, a third cylinder. That's what we're going to do, a fourth cylinder. So we're going to fill it up with little cylinders and find the volume of each one of those and then add them up. Okay, so it's an object. We have no idea how to evaluate. So we're going to approximate it by the sum of the volume of simpler object that we can really compute. Are you with me so far? So the question is, so cube doesn't work. Cube are not going to work in this problem. We're going to fill it with cylinders. So the question is, how are we going to generate those cylinders? We're going to fill it up with those cylinders. How are we going to generate and how are we going to get them up? Okay, so one way we can get those cylinder up is like this. So again, I am totally, don't write, I want you to listen. The rest is easy once you understand the concept. So one way we can generate the cylinder is as follows. We take those region, this is my A, this is my B. Okay, that's a way to generate them. And we fill it up with those rectangles, those usual, my rectangle, those usual rectangle. Basically fill it up. I'm just gonna put 4 of them, not more. And then I'm going to rotate every one of those rectangles. Okay, so if I rotate this rectangle, so this is the whole rotated region. And now what I'm going to do is rotate every rectangle. And so I rotate this rectangle. I'm gonna get the cylinder, okay, which is filling the region. And then I'm gonna take the rectangle next to it. So that's how I'm gonna generate the cylinder. And I'm gonna rotate it. That's my second rectangle. You guys see how we're generating those rectangles. And now I'm gonna rotate this one. and I'm going to generate another cylinder. That's how I'm going to fill it up. And then finally, since I only drew 4 rectangles, I'm going to take this rectangle and I'm going to fill it up, generate. So the way we are going to fill it with cylinders, so I fill it with those tiny rectangles because they are easy, and I rotate every single one of them. Every one of them will give me a cylinder next to another one, next to another one, next to another one. So you can imagine this solid here filled with little cylinder. Now, of course, there are emptiness, but when the cylinders are very thin, we can actually fill out the volume. Questions? Is the picture a little bit clear or not? If it's not, please let me know. Okay, so the way we're going to do it is we're going to take every rectangle, we're going to rotate each one of them, find its volume, find volume of this, plus the volume, plus the volume, plus the volume, add those volumes. So in your head is the region is filled with those little cylinders. We're going to add their volume. So that's really the idea we are going to proceed. And now let's start to do work. And it's going to be relatively easy. It's not going to be hard at all. So first, the book used the word disk. So let us define disk before I define this. So a volume of revolution. First, let's see what we mean by disk. Okay, disk is, sorry. What's a disk? Disk is nothing more than a cylinder. When you say disk, it's nothing more than a cylinder where the height is very small. The height is very small. The height is going to be usually the delta y or the delta x. Is very small. It means in your mind, I want you to think a quarter. You know what a quarter is? You guys have ever seen a quarter before? You know how thin it is? That's how I want you to think when you think a disk. So it is a cylinder where the height is very small. The height is going to be usually my delta y and my delta x. So it is really a cylinder. So when I think cylinder, I think about sorry, when I think of disk, I think about something like that. Very small height. That's a cylinder. This is the height here, which is, as I said, it will be either delta y or delta x, and this is the radius. Or you can think of it, that's very small, this is a disk. Okay, that's what we mean by a disk. And the volume of the disk, as your classmate said, the volume of the disk is area of the base, which is a circle, area of the circle, times the height. It means area of the base, it means pi times the radius square, that's the area of the base, times the little height. Okay, so that's what we mean by the disk. It's a very like a quarter. That's right, very thin. Now, our setting in this problem is the following. So let's see what the setting is. Okay. We start is with region R. Let R be the region. Bounded by the graph of y equal f of x the lines x equal a, x equal to b. And let S be the solid. S is the solid. Obtained by rotating R about the x-axis. S is called a solid of revolution because it was obtained by rotating something. It's called a solid of revolution. Okay, because we get it by rotating something. Question is, find the volume of S. Oh, okay, let's get going. So I draw the picture. So this is my function. That's f. As I said, f doesn't have to be increasing, nothing. So this is f. And we rotate. So that's the rotation right here. And we get something. That's the solid I'm talking about. This is my S. And we're going to get something like that. I rotate usually the end point. They give me an idea. That's the solid S. All right. And the question is, that's S. Find the volume. All right. So what we're going to do is we are going to cover the region. So this is my R and this is my solid. So we can cover the region R with quote unquote very thin vertical slices or vertical rectangle. And then rotate each about the x-axis. Okay. So I'm going to focus on one of them. I'm going to, as we do, we're going to take a typical rectangle, rotate it, and find its volume. And find its volume. Find the volume of each rotated slice. That's going to be the idea. All right, so let's do that. A typical slice. So that's my graph. This is A, and this is B. And I'm going to take a typical slice any place. As I said, instead of writing xi here, and the book does this, I will write x just to make the presentation easy. So this is the little slice that I'm going to rotate. From here to here, that's the delta x. Now, when I do those problems, I do two pictures. This, I leave it for labeling, and here just the pictures of the rotation, just to give you an idea in your mind what I am doing. So rotate a slice. So this is my graph, and this is my slice. Now I'm going to rotate this. What am I going to get immediately? When I rotate it, as you guys know, we're going to get the cylinder. And the question is, what's the volume of the cylinder? Okay. Of the disk. So volume of typical disk. Of typical disk. Okay. To find the volume of a typical disk, I need the radius. So what's going to be the radius? And I need the height. And then the volume. And we are practically done. All right. If I take this one and I rotate it, what's going to be the radius? Now I stop and I listen. The radius is going to be what? From where to where? That's going to be the rotated rectangle. The radius is going to be from here to here. So on this picture, where is the radius? That's why I keep this not rotated to label it. The radius is going to be from here all the way to here. That's the radius. So the radius is equal to what in this problem?
F of xi.
Exactly, f of xi, 100% correct. That's going to be my radius. That's the radius of the cylinder. What's going to be the height or disk? What's going to be the height of the disk? That's the height of the disk. That's the delta x. What's going to be the volume? Area of the base, as your classmate said, that's area of the base. It means pi times f of x squared times the little delta x. That's the area of the circle, of the base or the circle, if you want. You times it with the height. So every rotated rectangle, that's the volume. So the volume of the solid now is approximated by. Now I'm adding those that I drew a minute ago. At this stage, I'm going to add the volume of this plus, plus, plus. That's what I'm introducing back the xi to reflect that I'm going to add those. So it's going to be almost equal to the sum of the little volumes. It means at this stage, I put f of xi because now I'm thinking of splitting this into pieces and adding the volume. Times the delta x, I'm adding the little volume from y to n. This is the Riemann sum that I want. So now finally, the volume of the solid is going to be what happened to the Riemann sum when n becomes very large. So by the definition of the definite integral, it means we are adding pi times f of x squared dx, and always for the interval of integration, what I have to divide into pieces to cover the region, which is in this scenario from A to B. Now you don't have to memorize this formula, but any stretch of the imagination. The only thing I want you to memorize is the volume of the disk. Everything else, we should be able to figure it out by yourself. So I very, very quick. Suppose I tell you find the volume of the following picture. I will do that very quickly. I started with a cone, so why not a cone? So suppose I have the following picture here. Let me make up numbers. Suppose I put 1 here and 2 here. That's the region. And so that's region R. The question is, rotate R about the x-axis. Find the volume of the solid obtained. That's the plan. So as we know, when we rotate this, we're gonna get a cone. And my question is basically find the volume of this cone. All right, so I'll draw the picture again and we proceed. So this is my region, that's my emphasis. This is the point 1, 2, and this is my region here. And that's the one I want to rotate. Okay, to be able to rotate it, I take my little rectangle here. As you realize, at this stage, I forgot about anything called formula. and I rotate my rectangle. So when I rotate my rectangle, I'm gonna get my cylinder. So typical disk. Let's analyze the typical disk. So I call this little piece here X, and this is my delta X, typical disk. What's the radius? What's the height? And what's the volume? Once you figure all this out, you are done with your problem. Okay, what's the radius here? What's missing? What am I missing to give you the radius? The radius is from here to here. So am I missing something? Is there some info I didn't give you?
You're missing the actual function.
You're missing the actual function. Can you give me the equation of the function quickly? Who can give me the equation of the function? This is a straight line,
It's
correct? What's the slope? You go by 1, you go up by 2. So that's y equal 2x. So the radius is going to be 2x. So I did not give you the function because it's very easy. So I expect you to be able to do it. Absolutely correct, Grant. So the radius is 2x or 2xi, whichever you want to use is okay for me. The height is the little delta x. That's the height. The volume is pi times the radius squared times the delta x. So volume of solid is almost equal. Now in my head is the splitting. Pi times 2xi squared times the delta x, I equal 1 to n. As you realize, I don't need to memorize the formula. I just need to memorize the volume of a disk. So volume of the solid now is the integral of pi times 2x squared dx. And my interval, to cover this region, I need to go from 0 to 1. So finally, I will get pi integral from 0 to 1. 2x squared is 2x times 2x, 4x squared dx. And finally, you just evaluate this and we will get 4/3 pi. Because this will give me 4/3 x cubed, we get 4/3 pi, which is exactly the volume of the cone that you guys see in the picture. All right, that's it for today. Please do your homework for tomorrow. And as you know, tomorrow is your quiz and we will handle it exactly like last time. But please do not cheat on your quiz. It will not get you anywhere. Are you with me? Please be honest. I can't control you, but I have to rely on your honesty because your exam, you will have access to nothing except the piece of paper. Okay, any question before I let you go?
Professor Elias,
Yes.
so after our first test, the week after you should be back, or
I
are you
hope
like,
so. I definitely hope so. I definitely hope.
okay,
I'm trying, believe I'm trying my best.
no, you're good. Yeah, if you need more time, of course, it takes
Yeah,
more
I
time, but I
know.
was just wondering.
Yeah, I mean, they tell me that I can. That's what, they tell me that I can. And I hope I will be able to come back after your first test.
All right, awesome. Take as much time as you need. Have a good
Thank
one,
you,
Professor
guys.
Elias.
Okay, I have office hours right now. So please, guys, if you have any questions, stay with me. I mean, join my office hours. Okay, bye-bye, Shona. Bye, everyone.